This week we're going to start to look at chemical reactions more in the real world as opposed to on paper like we've been doing. So we've looked at chemical reactions, what types of chemical reactions there are. We've balanced equations and things like that. But if I were to tell you to go into the lab and run a reaction, I said to react copper nitrate with silver chloride. It may seem simple, but when you go to do it, the first question you're going to ask is how much of each? And so if we run a reaction in real life, we have to have numbers involved. And that's what we're going to start talking about today, these quantities in our chemical reactions. And so I think it's going to help if you imagine our chemical reactions and our reactions that we write out as being like a recipe. So this is something that you see all the time. If you want to make 16 pancakes, you need 3 cups of flour, 2 tablespoons of baking powder, 2 teaspoons of salt, and so on. But we could take this and we could write it in the form of a chemical equation. We could say 3 cups flour plus 2 tablespoons baking powder plus 2 teaspoons salt plus this plus this plus this plus this yields 16 pancakes. And it looks just like our chemical reaction. So it's easy to see it going that way. So when we see our chemical reactions for the rest of the semester, you can think of them, take them from that chemical reaction strung out format, and think of them as a recipe. These reactants on the left make the products, whatever you're making, on the right. So let's look at an example. So this is just the burning of propanes, and this is a combustion reaction. Okay, so we can look at this and show this multiple ways. So first, let's just look at the picture. So what this is showing is that we have some reactants over here and the products on the right. So in terms of a recipe, we generally figure out what we want to make and then figure out what we need to make it. So we want to make 3 carbon dioxides and 4 waters. So what do we need in order to make those things? It shows us that we need 1 of these C3H8 molecules and 1, 2, 3, 4, 5 oxygens. If you take these, put them in the oven, what you get out are these products. And so if you look at our reaction down at the bottom, that's exactly what it says. 1 C3H8 and 5 oxygens gives us 3 carbon dioxides and 4 waters. So this is our balanced equation. So we saw that the coefficients here, and you're familiar with coefficients with balanced equations, we saw that they actually refer to molecules, because these coefficients were the number of each type of molecule that were in the pictures. Remember that if there's no coefficient here, that it's an implied 1. The coefficient is referring to the relative number of reactants and products. For every 1 C3H8 that we had, we needed to react 5 oxygens. And for every 1 C3H8 we started with, we got 3 CO2s and 4 waters. That's exactly what this is showing us. For every 1 molecule of propane, C3H8, it's going to react with 5 molecules of oxygen gas, and it's going to make 3 molecules of carbon dioxide and 4 waters. But these coefficients not only apply to molecules, they also apply to moles. If we react 1 mole of propane with 5 moles of oxygen, we'll get 3 moles of CO2 and 4 moles of water. Numbers stay the same, The unit simply changed from molecules to moles. And so let's look at all the different things these coefficients can stand for. The first thing we saw were molecules. So 1 react with 5 to give 3 and 4. But what if we started with 2 of the propanes instead of 1? Remember that the balanced equation is always in the lowest number. If everything is divisible by 2, you have to decrease them by 2. So if we start with 2 instead of 1, what this means is that we have 5 times as many oxygens as propane. So we take our 2 times 5 is 10. We get 3 times as many molecules of CO2 out as we start with propane. So 2 times 3 is 6. 2 times 4 means we get 8 molecules of water. Same thing if we start with 100. 100 times 5, 100 times 3, 100 times 4. And so if we just increase that number, eventually we get up to 6.022 times 10 to the 23rd. And so you again multiply by 5, multiply by 3, multiply by 4. But 6.022 times 10 to the 23rd is a mole. So we can say that 1 mole of propane reacts with 5 moles of oxygen to give us 3 moles of carbon dioxide and 4 moles of water. We're going to start doing math problems, and these are not difficult math problems. The hardest part of them is remembering how to spell stoichiometry. Okay, so stoichiometry is using our balanced equation to calculate how much of each ingredient we need in order to make what we want to make. Or if we know how much of each ingredient we have, to figure out how much product we can make. Okay, so stoichiometry is something all chemists do. Okay, it's a hard word. At first, it's going to look hard. There's no way around it, but it's not. All stoichiometry problems are equally hard. If a problem looks hard, you're making it harder than it needs to be. All stoichiometry problems are simple. There are 4 types of stoichiometry problems. You can go mole to mole, grams to mole, mole to grams, grams to grams. And we'll go more over this in class, so you'll see what that means. Basically, we can work on a little flowchart here. So we're always going to start with the quantity of one thing in our reaction. It can either be a product or it can be a reactant. And the thing that we're starting with is always going to be A. We'll just call it A. And whatever we're trying to find out, we're going to call B. So if we know how many moles of A we're starting with, we can use what we'll call the mole ratio, and you'll see what that is. We can use this mole ratio to calculate the moles of B. Each of these arrows on this flowchart is one step in dimensional analysis. So the simplest reaction, or the simplest conversion you can do, is moles of A to moles of B. And now, if you go from grams of A to moles of B, as you'll see, it's the same thing. You just have to convert from grams to moles before you start. And you already know how to do that. So it's just tacking something you already know onto something new. Okay? So in this video, we're going to talk about moles to moles, which is the simplest one. And then in class, we'll do grams to moles, and moles to grams, and grams to grams. So a mole ratio is just the ratio of the coefficients. We use that to figure out the ratio of the number of moles of one thing to another. So there are 5 oxygens for every 1 propane. We already talked about that. 5 to 1 is the mole ratio of oxygen to propane. You just get them from the balanced equation. But it's important that you have a balanced equation. it's not balanced, your mole ratios are going to be completely wrong. So this is just what we looked at. The mole ratio of oxygen to propane is 5 to 1. 5 moles of oxygen to 1 mole of propane. We can say CO2 to oxygen is 3/5. There's 3 to 5. There's 4 waters to 3 CO2s. There's 4 waters to 5 oxygens. There's 5 oxygens to 4 waters. All you have to do is take the coefficient and compare it to the coefficient of another one. So if we know how much propane that we're starting with, okay, and we know the number of moles of propane, we can use this mole ratio to figure out how many moles of oxygen we need to react with it. It's just going to be 5 times as many. But we'll do this in a dimensional analysis format, because a lot of times the math isn't going to be these clean numbers like this. So this mole ratio is just a conversion factor. Remember, using conversion factors in dimensional analysis, that's exactly how we're going to use these mole ratios. So here it says we're going to have 0.40 moles of propane starting. So you take your 0.4 moles of propane, use your conversion factor, cancel your units. There are 5 moles of oxygen to 1 mole of propane. So we're starting with 0.4 moles of propane. We cancel units. Moles of propane go down here. The 1 goes here. The 5 goes here. Units cancel. We're left with moles of oxygen. So 0.4 times 5 equals 2. That's it. It's as hard as it gets. If it looks harder than that, either it's a tricky question, which I won't give you, or you're making it a lot more difficult than it has to be. And then all the other things, including grams, are just grams to moles conversions, which you know, or moles to grams conversions, which you know. So we've already covered the hard part. We'll just in class, we'll add on what you already know. I will see you there.